Hi, my name is Jerry Prince. I'm from Johns Hopkins University in the Electrical and Computer Engineering Department. I'd like to present our work on super resolution for anisotropic voxels in medical imaging. A common acquisition in MRI is one in which the in-plane resolution is good, that is the resolution in X and Y plane, while the through-plane resolution is poor, that's in the Z direction. In the past, people have acquired multiple acquisitions by rotating the acquisition and then combining those in Fourier space. It's a very common approach. But more modern goals try to do super resolution without acquiring multiple images so that you can save imaging time. As well, when you acquire multiple images, patient motion and geometric distortion become a problem. So there's a lot of past work in this area, most of them involving atlases. Now, we would like to not use an atlas. And what is an atlas? That's low resolution and high resolution image pairs, or potentially just examples of high resolution images. And the reason we want to avoid it is because atlases are sometimes impossible to acquire. In MRI, very, very high resolution data takes a very, very long time to acquire. And in many cases, it's acquired with low signal to noise ratio, which is not an appropriate target. As well, atlases tend to be acquired with a limited range of tissue contrasts. So if one wants to do super resolution on a different tissue contrast that might be new, for example, on the scanner, your atlas and therefore your trained super resolution method won't apply. So we would like to do it without atlases. As well, the 2D MRI example that I showed above is very common, and most people do not address aliasing in 2D MRI. I'll explain what that is in a bit. There is some past work on this, but this has not generally been combined in recent work on super resolution. As well, super resolution in MRI tends to avoid the scenarios where you have a very large anisotropy. For example, when the ratio between the through plane and the in-plane resolution is greater than 3. So we would like to consider these scenarios. Now, I want to back up a little bit and describe some basics in MR imaging so that I can explain what the needs really are. So in 3D MRI, this is an acquisition protocol that specifically uses Fourier space in 3D, and it scans a cube in 3D by sequencing through a series of Z encodes, phase encodes. The resolution that you get in the image after inverse transforming to image space is determined by the size of this cube, the dimensions of this cube. So the bigger the cube, the higher the resolution image that you're going to be acquiring. What is the goal in super resolution then in 3D MRI? Well, the goal comes from a typical ploy in acquisition, which is to reduce the acquired K-space in one of the dimensions, in this case the Z direction. Why would you reduce the number of acquisitions in the Z direction? Is to save time. But of course, by saving time, the resolution is reduced in the Z direction as well because you're not acquiring the high frequencies. This is often disguised when you get a scan because it's upsampled in the scanner by zero filling in the missing frequencies. That doesn't really change the underlying resolution, it simply changes the digital resolution. So what is super resolution? Well, we're going to learn a regression, a super resolution algorithm, in image space. We're not going to be learning it in Fourier space. I'm just illustrating things in Fourier space. But in image space, what we want to do is learn the regression that will have the effect of filling in the high frequencies in Fourier space. Also, when there's frequencies that have been attenuated in the acquired data, we also want to apply an inverse filter to that. 2D MRI is different. This involves slice selection and then scanning in 2D Fourier space after selecting the slice. And then this is repeated and a stack of 2D images is formed. So we're talking still about a 3D volume. We're not talking about just two-dimensional images. We're talking about 3D volume, but the acquisition is different. And as a result of that difference, the resolution and the way you think about resolution in 2D MRI is different. The slice thickness is, in fact, the through-plane resolution, and the size of the 2D Fourier box in analogy to the size of the 3D Fourier box, but in this case it's just 2D, determines the in-plane resolutions. Now, to aliasing. In 2D MRI, it's very almost ubiquitous to use contiguous slices where the slice thickness is equal to the slice separation. In this case, the sampling frequency in the z direction is the inverse of the slice separation. And this inevitably leads to frequency overlap, as is illustrated here. So when there's frequency overlap, obviously the higher frequencies in the acquired frequency box, which is shown in green, are corrupted. And when inverse transformed, these produce spatial aliasing artifacts. A point to note is that if the Z frequency content is low, that is, it's not involved in that overlap region, then there actually is no aliasing. And here's an example of what aliasing looks like. It's a higher frequency pattern that's not natural. Many people would call this a pixelization artifact, but it really is also a aliasing artifact. And you'll notice that in this area of the image, where the features are orthogonal to the image plane, then there are no such artifacts, and that's because the Z spectrum there has no high frequencies. So what is super resolution in this case? Well, we have an additional goal. So we have artifact-free low frequencies, and we also have frequencies that were not acquired. But in addition to the 3D case, we have now overlapping frequencies where they're corrupted. So super resolution, again, wants to learn and apply in image space a regression that will fill in the high frequencies and apply the inverse filter as needed in the acquired frequencies, but also restore the corrupted frequencies that are coming from that overlap region. So now I can get to the method that I'll be speaking about for the rest of the talk. This involves anisotropic acquisitions, and the point to note here is that when you look at these, you can readily see that there's high resolution information in the in-plane image, and there's low resolution information in any of the through-plane directions. So the data has both types of information in it, and then we can use the data to train itself. And in that case, the observed image is also its own atlas. The method I'm talking about is called SMORE. There's a 3D version that applies to 3D MRI, and there's a 2D version that applies to 2D MRI. In both cases, it applies to 3D data, volumetric data. But in the case of 2D SMORE, it has the additional task of carrying out anti-aliasing. I'll spend most of the talk talking about 2D MRI, which is really the unique part of this presentation. So I'm going to explain what's going on again in Fourier space, even though the regressions are carried out in image space. So the idea is that a true image would like to have a full spectrum, but what one observes is a low frequency version of that image. So the first step in SMORE is to filter that observed image in the x direction and produce a doubly blurred image. And from that, we can then learn a regression that takes us from that doubly blurred image back to the original image. That regression we learn in 2D using XY image patches. And we can use a standard 2D image super resolution algorithm. In fact, we use the Enhanced Deep Residual Network, EDSR, that won the super resolution contest in CVPR entire in 2017. We have some modifications. This is the basic network, but our modifications involve optimizing the patch size for our application. We removed batch normalization, removed the last ReLU, scaled the residual by a factor of 1/10, and our upsampling is not taken during the algorithm, but is done at the very beginning. So we're actually operating on full digital high resolution data from the very beginning. After some more optimizations, we found this works very effectively. So what is step 3? Well, we're going to take the observed image, which again has this limited Fourier content, and apply that same regression but in the through plane direction. Now it's a 2D regression, so we're going to apply it with image patches, in this case from the ZX plane, and then we need to apply that to all Y images. That gives us a estimated F whose Fourier content should be full. Now, SMORE can be viewed as a block diagram where you take the input image that's blurred in that vertical direction, G, and you apply the filter H to get a doubly blurred image, B, and then you train EDSR to do self-super resolution in the XY plane and apply it in the ZX plane to the original data. And this gives you your estimate. Now, there are a couple of points within that last presentation that one might wonder about. For example, why did we apply the filter only in the X direction? Well, in fact, when we're blurring the original image to create these examples for regression, we can blur it in any direction we want. So a series of rotations can be applied to get more training data and to learn that regression better. Well, the same thing can be done when we're actually applying the trained network. We don't have to apply it in the ZY plane. We can apply it in any plane that we want, so we can rotate the image around the z-axis and apply that regression. What this gives us is a series of estimates that are going to be subtly different, and we need to combine them. We chose to combine them in Fourier space, actually, using a technique called Fourier burst accumulation, which was reported for super resolution in cameras that have multi-shots, and you can combine those multi-shots to get a higher resolution version that you're imaging. So it ends up producing one self-super resolution reconstruction from that image. Now, before presenting results, I'm going to jump to the 2D version, which in principle is very similar and can be, in fact, implemented in an analogous way to 3D SMORE. But there's one step you have to add, which is the step that produces aliasing. So remember, G is filtered by H to produce this doubly blurred image B, but that image B did not have aliasing artifacts in the case of SMORE 3D. We need to introduce those, so you do that by sampling and then downsampling and then upsampling again to produce B tilde, which has both lower resolution and aliasing artifacts. We can then train the EDSR algorithm to produce a regression. That regression can then be applied again in the ZX plane or any one of those rotated planes that we talked about before. Now, we noticed when we did this that there was still evidence of aliasing in the final 3D image. And so in a heuristic experimental way, we discovered something that would quite reduce that aliasing a lot. And that is to introduce a second EDSR network that all it would do would be to try to reduce the aliasing in the blurry image. So you'll notice the inputs are B and B tilde. So this self-anti-aliasing network has the goal of inverting the aliasing that we introduced by this downsampling and upsampling. So the trick here is to apply that anti-aliasing step in the ZY direction, orthogonal to the direction we're going to apply the self-super resolution. And it turns out by experimental analysis that this works well. Now, we discovered that when the ratio between the through-plane and in-plane resolution is greater than 3, this is a good network to use. When it's less than 3, it doesn't make a lot of difference. And in order to save time, we would generally, for R less than or equal to 3, use the original SMORE 2D network without this extra anti-aliasing network. So here's an example for R equal to 4, where we've got the original B-spline interpolation in a zoomed region, an algorithm that was reported in 2015, that was really reported for smaller ratios, but had one example of this size, and JOG, which is one of our former methods, also a bit older, and the SMORE 2D results. So you can see that there's aliasing that's still left in the two results in the second and third columns, and one of the reasons for that is these methods were not designed to handle aliasing, but were really only designed to do super resolution. An even more dramatic example is when R is equal to 6, and you can see the effect of super resolution without incorporating anti-aliasing leaves much to be desired. We evaluated the usual metrics. Because this was a simulation, we could evaluate SSIM and PSNR, and as you can see in all of these different ratios, SMORE was on the top, was better than the other competing algorithms. Here's an example where we don't have truth. This is a marmoset brain. It's pretty dramatic because R is actually greater than the previous example, 6.6. And you can see in the B-spline interpolation quite a bit of blurring and also quite a bit of evidence of aliasing. Now, we've shown the middle column is SMORE 3D, where it does not consider anti-aliasing. And like the other two results I showed you previously, you can see that it doesn't perform very well. It leaves the artifacts in there, although it does tend to produce a higher resolution image. SMORE 2D nearly removes all of the aliasing artifacts that were originally present. This is showing you the image that I had shown you earlier to emphasize again that when you anti-alias this result, it's really reduces very dramatically the evidence of aliasing in the images. Now, SMORE is not perfect. We did notice some problems. One of them is that there's a fundamental mismatch when we learn the regression. If you look at the learning step, you're learning from a doubly low to a low resolution image, whereas when you apply it, you're applying it to only an image that has low resolution in one direction. And so there's something a little bit off about that. The regression that's going to be learned is a little bit off. That's, well, and another problem with SMORE is that it applies its regressions to slices independently and doesn't consider from slice to slice. And you can see some examples here that are circled, how that might lead to slice inconsistency in the results. So to address these problems, the first problem we are going to apply SMORE iteratively, where we realize that after the first iteration, after the first use of SMORE, the slices are thinner, and therefore they would represent better training data. So why not take the output of SMORE and retrain the network and then apply it to the original image? That's the first step of iSMORE. And then we can simply apply that again and again. Notice that we apply it to the original image, not the super resolution image, because we really don't know what the resultant resolution is of that image. And we would not know H, for example, for that image. Improving slice consistency works by applying a 3D network. We use the 3D version of the EDSR network. But because you're applying it on a rotated data set, it turns out that it doesn't work very well at the beginning where the resolutions are quite anisotropic. You learn it in one direction, apply it in the other direction, just like the previous inconsistency, the 3D network does not work well. So we only apply the 3D network after the first application of SMORE, where the slices are more nearly isotropic in resolution. So here's an example of multiple stages. We start with an original, and the first application of SMORE qualitatively looks quite good, but the second application you can see a few bits of improvement. Third application maybe not a lot of difference. We found that after this third stage we didn't see any improvements in any of the data that we tried. But in the 3D microscopy, this is 2-photon fluorescent microscopy of blood vessels. And this is a maximum intensity projection of these vessels. We did find quite a bit of improvement in those first three applications. So the first one shows you how degraded the resolution is in the through-plane direction, and how SMORE really does improve that resolution quite a bit, but you can see very strong evidence of this slice inconsistency in its application, and also not really as high a resolution as you would like to see in the through-plane direction. So in the third application, though, the in-plane and through-plane looks very, very similar. This is a blow-up, a zoom of the same example that I just showed you moments ago, where you can see in greater detail the evidence of that slice inconsistency. I'd like to acknowledge the people that have helped and the funding that have also supported the work from time to time. Thank you very much.